myself Ashwat Ayush. In this video, I am going to cover the topic of electromagnetic waves. What are electromagnetic waves? In general, we can say that the waves which are present around us are electromagnetic waves. One of such example is white light. The white light consists of 7 colors, the Vepcure. It belongs to the visible spectrum of the electromagnetic waves. Now, for the word electromagnetic, we can say that it consists of two words, electric and magnetic, electric field and magnetic field. These two physical quantities oscillate perpendicular to each other and they move in a common direction, which we call the direction of light. Now the question comes like how these two physical quantities can relate and how do they correspond to the electromagnetic wave. So to answer these questions, we will write an equation which will be the ultimate aim of this video. But to reach that equation, we will have to understand some mathematical tools and operators like del operator, divergence, curl, surface integral, volume integral, which will help us to understand the Maxwell equations. These Maxwell equations will finally help us to derive the expression or the equation of the electromagnetic wave. So let's continue. So let's start with del operator. Del operator is written as del by del x I cap plus del by del y j cap plus del by del z k cap. This will help us to understand the gradient, divergence and curl. Now let's talk about gradient. Gradient is a vector quantity. It is applied to the scalar quantities like any function. Suppose that we want to find the variation of a scalar quantity along x, y and z direction and scalar quantity like a function f. So we write it as gradient f is equal to del f by del x I cap plus del f by del y j cap plus del f by del z k cap. It says that how this function varies along x axis, y axis and z axis. Here the del operator and functions are just multiplied. There are no cross product or dot product between these two things. It's just like a constant multiplied with a variable. Now let's take the case of divergence. It is a scalar quantity and it is applied to the vector quantities just opposite to the gradient. The divergence of a function can be calculated as divergence f is equal to del operator dot f vector. As these two are the two vector quantities, on their dot product we will get a scalar quantity. For understanding the physical meaning of divergence, let's take the condition that a water is flowing through velocity v and we want to find that how much amount of water passes through this dv volume. To get the amount of water passing through this dv volume, we will use the concept of divergence. Here the vector v is the parameter, so the amount that passes through this dv volume will be given by the product of this volume and the velocity. So amount is equal to v dv. Now we will talk about curl. Curl is a vector quantity. It is applied on vector quantities, meaning this curl is a vector quantity and it is applied on a vector quantity, meaning del cross f. In the case of gradient we saw it was del f, then in divergence we saw it's del dot f, and curl is del cross f. We know that the cross product of two vectors is itself a vector, that's why curl f is also a vector quantity. The function f is written as f1 I cap plus f2 j cap plus f3 k cap. These are the three components of this function along I cap, j cap and k cap. The curl f in determinant form is written in this manner. Now to understand the physical meaning of curl, as the name suggests, it's curl. That means we will have something curly. So the physical meaning can be understood like if there is a bucket and we make a hole at its bottom, the liquid starts to come out of it and some curls are formed on the surface. It just drains in this manner. So the velocity vector of this water coming out is v and it's rotating in this manner. That means the curl of this velocity is this movement. Now let's understand the topic of line integral. Suppose that this is the path from point p1 to point p2 and this is the r vector written as rx I cap plus ry j cap plus rz k cap, and we want to find the how this function varies along this path. So by line integral we can get the how this function varies through this path. It is given as integration p1 to p2 f dot dr is equal to integration p1 to p2 and fx dx plus fy dy plus fz dz. As it was the dot product, so just after calculation we got this expansion. Now let's talk about surface integral. Surface integral is given by a physical quantity that passes through this surface area will give us the surface integral of this quantity through this area. Let's suppose the surface area vector is written as sx I cap plus sy j cap plus sz k cap. So its differential form is like dsx I cap plus dsy j cap plus dsz k cap. Now the quantity a in vector notation is like ax I cap plus ay j cap plus az k cap. So on their dot product, the surface integral will be calculated and it will be written in expanded form like this, and it will be integrated from 0 to s. The example for surface integral is like the magnetic flux that passes through a surface area. Here the magnetic field will be the quantity, and the surface area will be the this s vector. So as these two are in same direction, so their dot product will be positive, and it will give us the total magnetic flux passing through this area. Now let's talk about volume integral. Volume integral, suppose this is the volume V and this physical quantity A passes through this small dv volume. So a vector is written in vector form like ax I cap plus ay j cap plus az k cap, and v vector is vx I cap plus vy j cap plus vz k cap. In differential form, dv vector is written as dvx I cap plus dvy j cap plus dvz k cap. So on doing volume integral of this physical quantity through this volume v, we will write it in this manner. The example of volume integral is this point charge q which is placed inside a volume v, and electric field lines are coming out of it, and we want to find the flux, that is the dot product of this and the area vector, so which will be calculated using volume integral. Now let's discuss about the Maxwell equations. There are four Maxwell equations. The Gauss law for electrostatics. In this law, Gauss said that if we want to find out how much flux is coming out through a closed surface, we will have to make a Gaussian surface around the charge, and when this charge is divided by epsilon naught, it gives us the value of the electric flux coming out through that volume. So this E dot dA, this quantity when multiplied with area vector will give us the electric flux. So in this notation we can say divergence of this electric field is the equal to the charge density upon epsilon naught, which is similar to this one. We have seen that divergence is the area, no, the quantity that comes out through the closed surface. Suppose q charge is inside this surface, and its own volume is v, so its charge density will be given by rho is equal to q upon v. And as we can see that this charge will emit these electric fields, and on increasing the charge, the electric field lines will increase, thus the divergence through this surface will increase. Therefore we can say that the divergence through the surface is directly proportional to the charge density of this volume. Now let's discuss about the Gauss law for magnetostatics. It says closed integral of b dot dA is equal to 0, or del operator dot b vector is equal to 0. As we know that the magnetic field lines forms closed loop. These are different from the electric field lines which just originate from positive charge and terminate on the negative charge, but the magnetic field lines originate from north pole and they terminate at south pole. That means they form the closed loop. So, and divergence is the net output or input that is coming through the surface, as equal amount is outgoing and similarly same amount is returning back. Therefore the net output will come out to be 0. That means the divergence of this magnetic field lines will come out to be 0, which is uh, also discussed through this formula. Now we will discuss about the Faraday's law for electromagnetic induction. As we know that according to Faraday's law, the EMF induced is equal to change in magnetic flux with respect to time, and also EMF can also be written as V is also a symbol for EMF. So we know that the electric field when multiplied with the distance gives us the EMF. Now the suppose that we have these coils in which is connected with a galvanometer. As we bring a bar magnet near to it, the flux through these coils changes, which induces the EMF inside it. Suppose the bar magnet is approaching this coil, so the magnetic flux that passes through these coils increases with time. That means according to Faraday's law, it will try to oppose the change in its flux, so it will induce current in itself in such a direction so that it itself produces the magnetic field in the reverse direction, so that it can oppose the change. And electric field that is induced in the coil is the force or the motion of water in the bucket. Now we will discuss about Ampere's secretarial law modified by Maxwell. Before this law, these three laws were given by other scientists, but it was just compiled by Maxwell. But in this law, Maxwell himself also played a role. As we know in Ampere's law, whenever current passes through a circular loop, then magnetic flux through this loop is given by integral dot dl is equal to mu naught times the I net passing through this loop. In this case, as one current is going into the plane and one current is coming out of the plane, so net current is coming out to be 0. This was just an example for Ampere's secretarial law. The thing that Maxwell noted was that suppose we take a capacitor into our circuit and current is flowing through it, the charge will, as we know, the charge will get collected on the plates of the capacitor. This current that is flowing in the circuit is called the conduction current, but he also wanted to know what happens here. So to understand what happens at this place, Maxwell noted that this plate has charge q which is growing with time. Suppose at time t, charge q has came to this plate. So on making this Gaussian surface, we want to know what amount of electric field is passing through time. So at any time t, phi through it will be given by q upon epsilon naught. So on differentiating it with respect to time, so after differentiating it with respect to time, this dq by dt becomes the current, which Maxwell called it as displacement current. So this I displacement, on sending this epsilon naught on left hand side, we got epsilon naught d phi e by dt is equal to I displacement. Maxwell wanted to introduce this thing also in the Ampere's secretarial law, which just had this I passing in the circuit. So when he brought it into the formula, it became as mu naught I, the conduction current, plus the I displacement current that flows between the capacitor. Displacement. So the I conduction is just simply written as I, and this displacement current, as we got from this equation, is epsilon naught d phi e by dt. So similarly, this form is also interpreted in different method as this equation, where J is the current density and there is a curl in place of close integral of b dot dl, here it is the del operator cross b, which is curled, and we got same formula as this but with different notation. Now finally we will derive the expression for electromagnetic wave using Maxwell equation. For free space, Maxwell equation can be written in these four forms, that is del dot E equal to 0. As there is no charge in free space, so del dot E became equal to 0. Del dot B was earlier also it was 0, and del cross E is equal to minus del B by del T as earlier. The change comes here in del cross B, where there is no current density as there is no charge in free space. Now to solve the electric field component of the electromagnetic wave, let us focus on the third Maxwell's equation, which is del cross E is equal to minus of del B by del T. On applying curl operator on both the sides, it gives us del cross E is equal to minus of del cross del B by del T. As we know that this curl operator is independent of time, therefore it can go inside the bracket, and it can be written in this way. After using vector calculus on left hand side, this LHS becomes del into del dot E minus del square E is equal to minus of del upon del cross B by del T. From Maxwell's first equation, del dot E is equal to 0, so this part became equal to 0. Now this minus and minus sign gets cancelled. So, and again from fourth Maxwell equation, this del cross V is equal to mu naught epsilon naught times the del E vector upon del T. So we can substitute this thing with this value. So after bringing this upon left hand side, finally we reach us to the electric field component of the electromagnetic wave, which is equal to del square E minus mu naught epsilon naught times the del square E upon del T square equal to 0. Let's talk about the magnetic field component of the electromagnetic wave. On applying curl operator on both the sides of the fourth Maxwell equation, we get del cross B equal to del cross of mu naught epsilon naught times del E by del T. As we know that this del operator is independent of time, therefore it can go inside, and after solving the left hand side using vector calculus, we can write del times del dot B minus del square B is equal to mu naught epsilon naught times del cross E by del T. From Maxwell's second equation, we can say that del dot B equal to 0, so this left hand side reduces to del square B. Now minus of mu naught epsilon naught del times del cross E by del T is the result. Now on applying third Maxwell equation, this del cross E reduces to minus of del B by del T. So on substituting this at this place, these both negative signs gets cancelled, and del square B gets equal to mu naught epsilon naught times del square B by del T square. So on bringing this things to the left hand side, it becomes del square B minus epsilon naught mu naught del square B by del T square equal to 0. Both the equations that we got are same as a general equation of wave, that is del square U is equal to 1 by V square del square U by del T square. That means that these two quantities, that is magnetic field and the electric field, are the two constituent of electromagnetic waves that move in a wave pattern in a light, and they constitute the electromagnetic wave. So this was my video. Hope you enjoyed it. Thanks for watching.